Hello my dear students, this is Akash HD. Welcome to the ASD physics classes. Hope so you all are doing really great. So students, in this video we are going to learn magnetic force on moving charged particle based cases. You know very well, whenever the charged particle moves in a magnetic field, it experiences the force. Okay, this force can be zero also, this force can be maximum also, and this force can be between 0 and the maximum value also. In all these cases, charged particle will follow different trajectories, maybe straight line, maybe circle, maybe helical. Okay, so all these trajectories and their mathematical expression we are going to learn in this video. Okay, so let's go through it. The topic is, as I told you, magnetic force on moving charged particle. Okay, so here the magnetic force experienced by the charged particle is given by Q into V cross B. Okay, this is the charge here, Q, and here this is what? V cross B. This is which form here, students? This is the vector form here. Okay, this is the vector form. Now students, after that, if I talk about here the magnitude. Okay, so magnitude means we can write here like this: mod Fm is equal to charge Q. Depending upon the situation, this charge can be positive also and negative also. Okay, so here Q and mod of V cross B means QVB sin theta. Now, and students, this is the what? This is the magnitude. Now, can you see very well what is this, students? This is the magnitude here. Okay, now students, as I have told you very well, let's see here, where theta is angle between velocity and magnetic field. Now, which kind of trajectories? Let's see. Depending on angle theta, the charged particle can follow different trajectories like a straight line, circular, and helical in the region of a uniform magnetic field. Okay, let's go through it. Now we will see all these cases one by one. Now, so let's see here, students. The first one, case 1. So under the case 1, you can see very well, when a charged particle is moving along the direction of magnetic field, that means theta equal to 0 degree, or opposite to the direction of a magnetic field, we can tell theta equal to 180 degree, then the force experienced by the charged particle is 0. From the mathematical expression we can tell also. Okay, and hence it follows straight line trajectories as shown in diagram. Okay, students, so here I have taken here the magnetic field by the white color arrows in this direction. Now let's take, we have one charged particle. By default, I am taking here the positive charge particle. Okay, and this positive charge particle is moving along the direction of the magnetic field. So here we can tell very well, in this situation, how much theta? Theta is equal to 0 degree. Why? Because moving in this direction, that means this is the direction of the velocity and magnetic field in a same direction. Okay, similarly, if I take here the second situation, let's take, for example, the charged particle is here. Okay, and now let's take charged particle is moving in this direction with velocity v. So here what will be the angle? Magnetic field right side, charged particle, this charged particle moving left side. So here angle how much here? 180 degree. That means here it is moving along the field, and here it is moving opposite to the direction of the field. So in all these situations, we can tell here this magnetic force. What is here? QVB, either sine 0 or sine 180 degree, anything. And what this will come here? This will come here 0. How much force is coming here? 0 force. So whenever the 0 force is there, you know, from the Newton's first law of motion, what will be there? From the Newton's first law of motion, we can tell that here the velocity will be constant, or we can tell here uniform velocity. Uniform velocity. Now the charged particle will move with a uniform velocity. Uniform velocity means magnitude and direction should not change. That means in this situation, which path is possible? You can see very well, the only path is possible is a straight line, and here the charged particle will move with a which velocity? Uniform velocity. In which path? Straight line path. Okay, can you see very well? Remember that here, uniform velocity, net force 0, straight line path. Now next one, students, very important, very important here. Now put the star sign even. So can you see here, when a charged particle is moving normal to the direction of the magnetic field, that means angle between magnetic field and velocity, how much here? 90 degree. Then the force experienced by the charged particle is a maximum, and hence it follows circular trajectory as shown in diagram. Theta equal to 90 degree. Which trajectory? Circular trajectory. Let's see here how it will happen that here. So see first one here. See radius of circular path here. Na? So first let's see here. Here what will happen that here? This magnetic field is inside the board here. Na? That means along the negative z direction. This side x-axis, y-axis, towards your screen z-axis, and inside of the screen negative z-axis. Okay. So the magnetic field is along the negative z-axis. So remember that here. Magnetic field is inside, na? See, I'll draw here. See, the magnetic field is inside here. This is the magnetic field, and let's take it is moving in a at this point. Na? Let's take it. I have taken this point here. Na? So velocity is this direction here. So you know very well the magnetic field is inside, and anyhow the charge particle is positive only. Okay. So it will experience force in which direction? I told you F equal to Q V cross B. We have to curl our finger from V to B through the smaller angle. Now, so see like this. V this side, B inside. So V to B means thumb is going in which direction? Downward direction. Okay, like this here. See, downward direction here. Now, so this will be the force. This will be the force. You can see very well, students, here the angle between velocity and the force. How much here? 90 degree. So whenever this kind of situation exists, what will happen that here? It will follow the circular path here. Always, even at all the points, you know what will happen? Even at all the points, let's take this is the velocities. This is the velocity, instantaneous velocity. Is it? Like this it is moving here. And what will happen that here? It will experience one force, as I have told you very well. What is the force? This one here, force, magnetic force. Now at all the points. Here I have drawn here only 4. But at each and every point this will happen that here. Okay. And you know very well, whenever the particle will move in a circular path, it requires one centripetal force, and here this magnetic force represented by the blue color will act as centripetal force. Okay. And this R is the radius I have taken now. So in this situation, what can you write here? Remember that here as this magnetic force will act as a centripetal force. Magnetic force formula, kindly see here. QVB sine 90 degree here. Is it? Sine 90 degree, and centripetal force formula, kindly see here, mv square by r. Okay. Now, what other things will cancel out here? Kindly see very well. From this v, this one v is cancelled. So when I will write here r equal to mv by bq. What is coming here, students? R equal to mv by bq here. Okay. See, I will put here in a box also. Okay. Kindly see very well. This is the radius of the charge particle. Okay, R equal to mv by bq. M is the mass, q is the charge, v is the water, speed of the charge particle. If direction we are not considering, direction considered means velocity. Okay, remember that. Now students, after that, if we talk about here, very important, different forms of radius. So first one, see, in terms of speed v, I can write here R equal to mv by bq. What is coming? R equal to mv by bq. If in case in the question they told like speed of the particle is constant. Okay, so if in case speed is constant, we can write here R directly proportional to m by q. I am considering speed and magnetic field both is constant. Like that they will tell in a question here. So if in case v, now see here, this v and b both constant, then we can write here R directly proportional to m by q. Okay. After that, if we talk about here next one in terms of momentum, P equal to mv. So see here R equal to this mv will become P here. So I can write here P by bq. Okay. And if in case what is constant, let's take they have told momentum and magnetic field both is constant. Okay. Then this will become here R inversely proportional to q. Remember that here. Here what is constant? I told you velocity and the magnetic field. Here what is constant? Momentum and the magnetic field. If in case constant in a question used to come based upon the proton, neutron and alpha particle. Okay. And after that in terms of kinetic energy. Okay. So maybe in 11th, not maybe, definitely, we have seen the relation between kinetic energy and the momentum, K equal to P square by 2m. Okay. This was the relation. So from here, if we write here, what we can write here, see, R equal to P will become here root 2mk by bq. Okay. And if in case what is constant here, the kinetic energy and the magnetic field, because magnetic field anyhow it is a uniform magnetic field, constant only. Okay. So what this will happen that here, see, R directly proportional to, see here, root 2m by q here. Actually 2 is also constant only, now. So we can write here just root m by q, now because 2 is also constant. Is it? Next one, students, if we talk about here in terms of potential. So you know very well this kinetic energy means we can write here Q into V also. Okay. K is the kinetic energy, Q is the charge, V is the accelerated potential or accelerating potential. So in this situation, what will happen that here, remember that here, when you will put the formula K equal to QV. Okay. So it will come here, remember that here, 1 by B root 2 Vm by Q. Okay. This will come. And let's take here potential is constant, anyhow magnetic field is uniform, B constant. Then what will happen that here, kindly see very well, R directly proportional to, students, it will become here C root M by Q here. Okay. So all these basics we should remember that here. See this boxes I am drawing here. See, is it? This is second boxes, no? This further boxes is important when we are solving the numerical here. Is it? Kindly see very well. No, this boxes. Very, very important topic. That's why we are learning in a very, very detail here. Is it? And here we can't draw the box, so I'll draw here like this here. No? Kindly see very well. Is it? And how the numerical will come from this topic? I am telling you. Is it? So see here. They will give proton, okay, and they will give deuteron, no, and they will give alpha particle. Double ionized helium. Ion is called alpha particle. So if we talk about here the mass used to be M, 2M, 4M. Charge used to be E, 2E. Okay. So students, this basics you have to remember that here when the numerical is coming here. Okay. See here. Now after that we will go to the next one. Let's see here. Now students, if we talk about here the time period. No. So time period formula will be what? Remember that here in a circular path. It is given here T equal to 2 pi R by V. Okay. So I can write here, see, 2 pi by V, R value, you know very well, mV by BQ. Okay. So what other things will cancel out? Can you see very well? This V and this V is a cancel. Okay. So we can write here, see, T equal to 2 pi M by BQ. What is there, students? T equal to 2 pi M by BQ. Later we will learn that this time period is independent of the speed and radius of the charged particle. Okay. Because you know very well, again I am writing here, see, R equal to mV by BQ. Now, and here you can see M by, what is coming here, students? M by Q. So if I write here M by Q, from here M by Q, I can write here RB by V. Okay. This is very, very important. Why? Because here, without changing mass and the charge of the particle, R and V value cannot be changed. That's why we used to tell that here this time period is independent of the radius and the speed of the charged particle. After that, if I talk about here the angular velocity, so this used to be omega equal to 2 pi by capital T. Okay. So when I will put the value of the capital T, what this will come here, see here, 2 pi by 2 pi M by BQ. Is it? So what other things will cancel out here? See, this 2 pi cancel. So what this will come here? It will come here omega equal to, see, BQ by M. Okay. Angular frequency or angular velocity. Now next one, see, frequency. This frequency I can write here F equal to 1 by T. Even we used to tell linear frequency, angular frequency. So 1 by T will become what here? Can you see here? BQ by 2 pi M here. Okay. So I hope so all these things are very, very clear to you. This is the time period of the charged particle. This is the angular frequency of the charged particle, and this is the frequency of the charged particle. Okay. Can you see here? Very, very important. Now, and all these things, whether this one, independent of the speed of the charged particle, radius also. Okay. Great. Now students, after that we'll see here the important points here, very, very important points used to come directly in exam. Can you see here the first point? In circular path, speed and kinetic energy of the charged particle remains constant. Why? Because I have told you here, like if you remember, see, the velocity was this direction, no? The magnetic field was inside, and see here, the force, magnetic force was acting downward direction. Previous I have told you, is it? So angle between velocity and the magnetic force, how much here? 0 degree. So as the angle between velocity and magnetic force is 90 degree, not a 0, 90 degree here. Okay. So here what will happen that here, in this situation we can tell angle between force and instantaneous displacement also how much here? 90 degree. So in this situation magnetic force will not do any work. So if it is it is not doing any work. That means from work energy theorem we can tell that the energy of the particle is constant kinetic energy. Okay, so speed is constant, kinetic energy is constant. Which kind of circular motion? Uniform circular motion. Okay, remember that. Here second one, see, in circular path velocity and momentum of the charged particle changes due to change in direction. You can see very well the direction is keep on changing. Here it was there, left side, downward, right side, upward. Remember the directions? That's why momentum and velocity both will change. Next one, as I have told you, see here, third one, the time period, angular velocity and frequency of the charged particle is independent of its speed and radius of circular path. Is it? So all these things I have told you. Okay, very important. Now students, great. Now next one, let's see here the case 3. What is the case 3? We have seen straight line path, circular path. Now case 3. Here what will happen? See, when a charged particle is moving at any angle except theta equal to 0 degree, 90 degree and 180 degree, then component of velocity along the field gives straight line path. Remember that here. And the component of velocity normal to the field, that means perpendicular to the field, gives circular path. Hence the resultant path of the charged particle is helical trajectory as shown in a diagram here. Okay, so you can see here very well. Here I have taken here, let's take here, this is the magnetic field here. Is it? And here is the one charged particle. And charged particle is moving in this direction, making how much angle here? Theta. So angle between magnetic field and the velocity, how much here? Theta. This is not 0, not 90, not 180 degree. Then what will happen right here? See, in this direction, velocity component, I will write here V parallel, this will be V cos theta. No. And in this direction, velocity component will be V perpendicular, that means V sin theta. Okay. So according to this, the trajectory should be what here? See, according to V parallel, the trajectory should be straight line path, SLP. According to this, the trajectory should be circular path here. Okay. So when we'll combine both of them, straight line path, circular path, which trajectory will be there? Helical trajectory. That we will see that here. Okay. But the radius of the circular path, remember that here, R equal to which component is responsible for the circular motion of the charged particle? This perpendicular component, angle between V perpendicular and beta, anyhow 90 degree here. Is it? See, this one, this angle, is it? So this one is responsible for the circular path. Remember that here, M V perpendicular by BQ, or we can write here MV sin theta by BQ. If you put theta equal to 90 degree, you will get here the second case here. Is it? So remember that here, no? Very important, radius. No, can you see here? Okay. Now students, after that, if we talk about here this one, time period, it will be as it is. Remember that here, T equal to 2 pi m by BQ. Okay, because independent of the speed here. Omega will be what here? Remember that here, it will be BQ by m, same story. And angular frequency, F will be how much here? 1 by T. That means it will be BQ by 2 pi m here. Is it? So all these things will not at all change here. Is it? Remember that here. This thing as it is, same only here. No? Because all are depending upon here, there on capital T, and it is independent of speed, or we can tell if we include the direction also, so velocity. Okay? Remember that. Next one here, students, the pitch. Very important term. See, it is defined as the distance traveled by the charged particle along the magnetic field in one complete cycle. Okay. So what will happen that here? Straight line path, circular path, what will happen? The charged particle, just like a spring, it will move in a which path? Helical path here. Okay. So let's take, for example, if I take here at any instant, here time is t equal to 0. After completing like this, one circular path, t equal to capital T. Okay. So it will travel some distance in the direction of the magnetic field in this direction B. Okay. And it is moving like this here. Is it? Moving like this. No, like this. So it is following which path? Helical path. And this pitch is given by, you know very well, distance equal to speed into time. Okay. So here I can write here, see this pitch, P equal to, remember that here, speed into time. This pitch, P equal to speed into time, or we can write here basic formula. First we'll write here the distance. Okay. So here the distance distance is equal to speed into time. So I can write here this pitch P equal to speed, how much here? This V parallel component, na? In this direction component is there, V parallel, na? Because of that only the charged particle is having the tendency to go ahead here, and into time period T. So here I can write here this P is equal to V parallel is V cos theta T, means 2 pi m by BQ. Okay, and here just remember that here I will put into the box here, important. And if I just talk about here the special case, what is the special case? For example, if I talk about here the case 2, na? Which path was there? If you remember, circular path was there, na? Circular path. So in case of circular path, remember that theta was how much here? 90 degree, is it? So in this situation I can tell that here, hence pitch value how much here? You know, theta equal to 90 degree, cos 90, 0. That means the plane of the circle will not change, na? If starting from here, after completing, again it will reach to the same point, it will not go ahead. So in case of circular path, pitch how much here? 0. Kindly see very well. Is it? So students, I hope so. This video based upon the different trajectories of the charged particle is very clear to you. Keep studying, keep growing.